You made that in the first 2 weeks.
No.
Yeah.
No.
Where are the warm-ups?
Yeah, a little bit.
Warm-ups.
They're really finishing in class, so I don't know what you're doing.
We're having guaranteed
I'm pretty sure.
Well, make it about
One of their big three,
Sorry, I'm thinking of 6 hour. Forget what I said. What happens when I do you guys different stuff? All right. So here's the deal. Your warm up for today is going to be this.
It's the week of
7 all week.
7.
This is your warm up. Okay, cool. So the idea is, I zoomed in as much as I could. You've got 7 red squares, 7 green squares, and 7 yellow squares.
What's the last
Your
one?
there is 7. There's this tiny little one right here. 1, 2, 3, 4, 5, 6, and then 7. I zoomed in as much as I could. It won't let me zoom anymore. I have zoomed as much as I can. So your job is to figure out how much of the entire square, the big square, right? The biggest of all the squares. How much of that area is colored in red? How much of it is colored in green? How much is colored in yellow?
I already know the answer.
Wonderful. Keep it to yourself. The answer's not what matters. It's the thought process. I'll give you a hint. If you notice, if we ignore the craziness that's going on right here, we've got 3 squares that are colored in, other than this ridiculousness, right? So this is a quarter. The first red square is a quarter of the whole darn thing, right? So what does that mean this square is? Well, that's a quarter itself, and that's a quarter of a quarter. When we say the word of, we mean multiplication, right? So if I want to know a quarter of a quarter, I write it like that. Remember, we multiply across with an A. No cross multiplication, that's not allowed, that's not a thing, we don't do it. Across would be 1/16. Of course, right? So we have a quarter plus a 16. The red. And so on and so forth. We've got 7 different squares there.
Wait a second. So you're supposed to figure out what each of these are?
So sit down and I'll explain.
Hang on, I want to count the boxes.
There's 7. 7 red, 7 green, 7 yellow. I already said, so sit down. So,
Yeah, I wrote my paper.
7 red, 7 green, 7 yellow. All of them are squares. Figure out the total area that's colored in red, the total area that's colored in green, and the total area that's colored in yellow. You're going to have 4 minutes to do it. The song of the day is super stupid. I would like to dedicate this song to all of you. Again, the song is Super Stupid by Funkadelic. Funkadelic is a band that came about by George Clinton. I talked about him before in here. Crazy guy. He had a band named Parliament. And then that combined with his other bands, and they created this band called Funkadelic. It is funk, and it is psychedelia all combined, so thus Funkadelic. The album is Maggot Brain. You've seen the picture on the screen. It's this woman that's buried up to her neck screaming. Fantastic song, fantastic album. The song is Super Stupid. Hey, you guys want to try Let's talk about it. Anybody have a strategy that they use to figure out the area? Taken up in red, taken up in green, taken up in yellow? Any interesting thoughts? Yeah. Why?
That's what I said.
Yeah. Oh, so y'all screwed up.
Let's go.
So this is valid, right? To take a quarter of a quarter of a quarter. What you get was a quarter of the whole area, right? Plus a 16th of the whole area, plus a 64th of the whole area, plus 256th of the area, right? And you keep adding that all up, you get Kamigami's to go down that route. We're going to do that. However, you should know what the answer is already. It's going to be a third, right? Because we have 3 colors, and each area is equal, right? There's 7 red squares, there's 7 green squares, there's 7 yellow squares, and the area for red, yellow, and green is all going to be equal. So it's a third, a third, and a third. That's it. Now, let's prove that algebraically. Not a fan of that, huh, Katie? How was homecoming, everyone?
It was
Crappy?
It was awesome knowing you were there.
Aww. I got to see you guys, so you guys are all morons, posting stuff on the IG, on my math account that I have on there, right? You guys followed me, I followed you back for that cloud, right? So I got to see all your pictures, and first I was like, oh, good God, I don't want to have to see this, right? And then second of all, it was like, aw, babies, growing up. So adorable. It was like a proud parent seeing y'all in there. And I got to see, like, and I only know you guys in context of this class, right? So, like, when I see you hanging out with other kids from other classes that I teach, it's like, oh, that explains so much. Man. Right? Yikes. Yikes. It really all makes sense now. Some of y'all could do a lot better, okay? Let me just put it that way. All right, here we go. Oh.
Yeah, we heard about that.
Jewel?
Yeah, you
Like the place where you go shopping for groceries? It's like my favorite place to shop for groceries. Yeah, Jewel. Jules. All right, so anyway. Here we are. So if we're going to do this, drawing a picture might help. Some kind of square, right? Quarters, 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 quarters. Anybody play quarters? Quarters. All right, on and on and on. There's 7 of them. So right here, which I believe was red, but if it's not, who cares? Is red. That's red. That's red. That's red. That's red. Right? On and on and on. We've got some yellow in here somewhere. I believe it was the bottom right. I could be wrong. And on and on and on. And then we've got green. Right? Very Rastafarian right now. Okay, so that's a quarter of the whole thing, right? Right? Cool. So that's a quarter. That's going to be a 16th. And again, we figured that out on the board, right? A quarter of a quarter is, in fact, a 16th because we multiply across with an A. Then we've got a 16th times 4. What's 16 times 4? 64, guys. 64. Because 16 times 4 is the same thing as 8 times 2 times 4. And you know that 8 times 8 is 16, right? Or, sorry, 8 times 8 is 64, right? Okay, cool. Play with your numbers. All right, easier way to think about it. 16 times 4 is just 8 times 2 times 4. 8 times 2 times 4, well, that's just 8 times 8. Cool. So that's 64th. What's 64 times 4? Let's do that in our heads. What's 60 times 4? 240. So we did 60 times 4 and got 240. How many groups of 4 was I short? This was 60 times 4, right? I need 64 times 4. So how many groups of 4 was I short? How many groups of 4 did I shortchange myself? 4 groups of 4, right? I need 4 more groups of 4. Because that'll get me 64 times 4, right? 64 groups of 4. Right? What's 4 times 4? 16, they all said. All right, and then 240 plus 16 is 256. So I did that in my head. I don't know about the rest of you. But I did it in my head by rounding. Instead of doing 4 times 64, I did 4 times 60, which is 240. And then I said, well, I need 64 groups of 4. I only did 60 groups of 4, so I need 4 more groups of 4, right? So I add 16. Yes? Sometimes. All right, 256 times 4. That's going to get us our 1, 2, 3, 4, 5th square. What's 256 times 4? Well, 256 times 4 is hard to do, but we could do 250 times 4, couldn't we? What's 250 times 4? 1,000. Now, how many more groups of 4 am I short? 6 groups of 4. What's 6 groups of 4? 1024. Nope.
All right. Besides
11. What's 1024 times 4? Well, what's 24 times 2? What's 48 times 2? Well, that's 50 times 2 minus 4. 96, right? So this is going to be 4,096. One, 2, 3, 4, 5, 6 squares. We need one more. So we need to multiply that by 4. It's going to be 1 over, what's this times 4? Well, 4,000 times 4, what's that? That's 16,000. Now, I need 96 times 4. How can I estimate that in my head? Go ahead. 100 times 4. Very good, because I overshot, didn't I? So 100 times 4 is 400 minus 16. 386. 384, I should say. Add them together. 16384. Now we gotta add them all up. How do we add fractions? How do we add fractions up? That's right. Can we just add a half to 2/3 and say that it's 3/5? Do we just add across? We do not. We multiply and divide across, actually. Division, you can't actually divide across. But here, it's not going to work. Right? We know a half plus 2/3 should be definitely more than 1, right? 2/3 is more than half. There's a half. That's going to be more than 1. I got 3/5. That ain't it, right? So what we need to do is get some common denominators. We need to have the denominators match. We need to talk apples to apples here instead of apples to oranges, right? He's talking halves. He's talking thirds. We need to get him to talk the same language. So what do? In this case right here, how many thirds are in a half? Ooh, hard question, right? Doesn't work. Right? I mean, there's 1 and some change, right? 1 1/2 thirds in a half, actually. Easier way to think about this is like, hey, look. What if they both had a common language to speak, like 6, right? 2 times 3 gets me 6. 3 times 2 gets me 6. That'll make them match, right? How many 6ths are in a half? 3 6ths. That checks out. And there's 4 6ths and 2/3, right? Because there's 2 6ths and 1/3, right? 1/3. And then it must be 4 6ths and 2/3. So really what I'm talking is 7 6ths, which is over 1, which makes sense. Okay. So we need common denominators. Common denominators here. Well, the rule is we want to go to the smallest value possible. So our smallest value is this guy, 1 over 16,384. So how do we make common denominators out of that? Yikes, right? Nah, it's okay. 1 over 16384 is going to stay. How do I make that common denominators with that? Well, how did I get this number to begin with? How did I get that number? Yeah. I did. So what number do I need to multiply this by to make it be that? By 4, right? So it's going to match up. I don't need to do the math in my head. That's why I did it, right? And so instead of 1, I'm going to have 4. Right? One of these guys is 4 of those guys because I have to multiply that by 4 to get that. Okay. Here, again, I want common denominators, so they better be the same. I can assume that. But in order to get this guy to be this, I had to multiply him by 4 to get to here, right? And then I multiplied by 4 again to get to there. So I multiplied by 4 twice. Really, I multiplied by 16. I multiplied by 4, and then multiplied by 4 again. So it's going to be 16, not 8. This guy. Multiply by 4, multiply by 4, multiply by 4. Multiplying by 64, aren't I? Okay. This guy. Multiply by 4, multiply by 4, multiply by 4, multiply by 4. What's 4 times 4 times 4 times 4? 4 times 4 times 4 times... Oh, it's 256. We already did that earlier, didn't we? 4 times 4 times 4 times 4. So I'm multiplying by 256. Do you see the pattern? Do you see it? That's right. This guy. I'm going to multiply by what, Zayden? That's right. And that's going to get me this. Last one. Going to multiply by 4096. And now they have all common denominators. So our answer is going to have a common denominator of 16384. Let's add these up. Let's get some easy numbers to put together. How about this one and this one? What do they add up to? Anybody? Oh, whoops. 4100. Right, I add 4 to this. 4100. That's not a 9, it's a 0. Cool. What about these two? 1040. These ones aren't as nice, but they still work out. Let's add those two together. And then 1, right? And 1. So that's 1, 6, 4, 5. Right? You guys said it should be a third, right? The red area should be a third. So does that reduce to a third? Zayden? Why not? Yeah.
Because a third goes on infinity, and that it leaves a remainder of 116,380.
Maybe. Hello, Cheyenne. So happy to see you. Is 5461 divisible by 3? Thank you very much. Is this number divisible by 3? Did we goof? It's not, because 9 plus 7 is 16. 6 and 1 makes 7. That's not divisible by 3. So what the heck? Did we goof? That's right. Looking at the picture, it should be thirds. So Zayden, you say it can't be thirds because third goes on forever. So I'm going to blow your mind. Here's a rectangle. And I'm cutting it up into thirds. Are they not thirds? So Zayden says this can't possibly be a third, and a third. Well, I mean, it's just a drawing. Just a drawing. If they aren't a third, then what are they? I know they're not actually thirds because they don't look like it, right? It's not drawn to scale. Zayden, I'm going to have to disagree with you.
Oh, wait.
Yeah.
There's 7 different markings, so that means there will be, you can't make 1/3 into a 7.
I guess.
It's a good idea. Good conjecture. Did we goof? And how do you know you didn't?
Each time you divided the square in the upper right-hand corner
Everybody hear what Jess said and understand it? Check it out.
We added one more.
Check it out. Check it out. Check it out. So if I've got a square, beautiful, and I cut it into quarters, now we're here, and I cut that into corners, now we're here, now I cut that into quarters, now we're here. Now let's stop because it's just going to get small. It's going to be hard to see. We said this is green, that's green, that's green. You see it now, don't you? I had a dream about this like about a year ago. It's amazing. I love when that happens. All right. There's an extra box. Oh! So it's not a third, and a third. It's like a little less than a third, a little less than a third, a little more than a third if we're considering that green, which we ain't, because it's that. A little bit less than a third. How much less than a third? Well, you said remainder under what?
Remainder of 160,300.
Okay, so turns out 13 goes into both these numbers except with a remainder of 1. It's really, really close. Do you know how many times 13 goes into 5, 4, 6, 1? Do you know how many times 13 goes into 5, 4, 6, 1? Let's estimate! 3 times. 13 times 3, probably at least 3. It's got to be at least 3. Okay? So let's try that. 5, 4, 6, 1. How many times does 13 go into it? Let's estimate. 13 times 100. Good estimate or bad estimate? Bad estimate. 13 times what? What do you want to do? Times 1,000? Well, we're going to get 13,000. Way over. Yeah. 40? Yeah. Well, that's going to be less. We need more. We already did 100 and it wasn't big enough. 500. All right, so we have 5 times 10, which is 50, plus 15 is 65. So we got 6500, right? Too much. 13,400. Let's estimate that. We get 4 times 10, which is 40, plus 12 is going to be 52. Ooh, that's pretty close. So it's going to be 13 times 400 and something.
25.
So that's 13 times 400. We need 20 more 13s. So 2 more 13s is 26. Add a 0 on the end.
Oh my god. That is definitely planned.
Oh yeah. He did that on purpose.
Wait, where's the 42069 IQ?
It's back there.
Oh, there it is.
I'm on a whole nother level. I'm playing 5D chess. You guys are down here, right?
You need to get Hunter Newman. You need to get Google in here.
He's playing checkers, we're playing chess.
Other way around, bud. Like the big brain move is actually checkers versus chess. Like you go back
You
to the
need
small
Siri
brain.
in here.
That's the big brain. Yeah, so big brain move.
Yeah, Hunter Newman.
Did I ever tell you the one time I gave an exam where all the answers were 420 and 69? That was amazing to watch unfold. The sheer terror on their faces, but also comedic relief. Great day. Great day.
I want to take that.
420 out of 69 would do again. All right, so.
You're challenging me now.
So remainder 1 under 13. So it turns out that another way to think about remainders is this. It goes into 420 times with a remainder of 1. We divide it by 13, right? And 1/13. So that's how much the red area is. Sort of, right? Wait, what? How much is the red area? No. The red area is this. Is 5461 a prime number? Is there no way to simplify this? I'm not going to explain why today, but I'm going to tell you something. Okay? Let's pick a prime number, 23. It turns out you don't have to check every single number between 1 and 23 to make sure it's prime. Maybe you can realize why. But if you check every number less than root 23 and it doesn't show up as a factor, it's prime. So if you root the number and you check every number underneath that, what's root 23 approximately? Let's do that in our heads. What's root 16? 4. So that's undershooting. The next root up is root 25, right? That's 5. So it's between 4 and 5. So let's say approximately 5. Okay? It's really close to root 25, isn't it? Right? So it's probably about 5. If we check every number between 1 and 5 and don't find a factor, we know, hey, look, it's prime.
Does 2 go into 23? No. 3, no. 4, no. 5, no. Oh, it must be prime. Now that's a lot easier than checking all those numbers, right? What about this guy? Somebody tell me the root of 5, 4, 6, 1 approximately. At least 6. At least. Well, the root of 144 is 12. So it's going to be bigger than that. Correct me if I'm wrong. About 32?
32 times 32.
32? I might be wrong. What's the root of 5, 4, 6, 1?
Why isn't my calculator?
Take your time, anybody.
Mental math.
Xavier, you got the answer for me? What's the root of 5, 4, 6, 1?
Somewhere between 70 and 70.
Type it into your phone and then put your phone away.
That's what I'm doing right now.
Awesome, what you got?
32 would be
As far as I know,
The square root of 5,461 is approximately 73.8986.
Okay, close enough.
yeah. Slaughter.
Okay, so we need to check up to 73. It could be worse.
73.89857914.
Boring, no one cares. All right, so
6926.
we'd have to check up to 73. Is 5, 4, 6, 1 a prime number? You know an easier way to check? Well, if we're going to use our phones, if we're going to use calculators, just ask, is 5, 4, 6, 1 prime? You can look at a table of primes.
Is 5, 4, 6, 1 prime.
You dinguses.
Here's what I found.
No.
There was primes. 5449, 5471.
So it's not prime.
No.
Well, they both have to share a common factor if they're going to reduce. What is that common factor? Be anything between 1 and 73. Anybody got a clever way to figure it out?
Let's just wing it. I'm thinking 1 would
Would 2 work for either of these guys? No, right? So what does that tell us? Neither of them are going to have a prime factorization of 2, right? Meaning that none of them are going to be even. So we just eliminated half the numbers between 1 and 73. We don't have to check the evens. That's nice. Do we have to check 5 or 10s? No, so we just eliminated 5, 10, 15, 20. None of those are going to work because they don't end in a 0 or a 5. Are either of them divisible by 3? No. So that means all the factors of 3 are going to be eliminated. So we've eliminated factors of 2. We've eliminated factors of 3. We've eliminated factors of 4, 5, you know, all the evens, right? We've eliminated 5 and its factors. What about 7? We don't have a trick for 7. I know a trick for 7, but I'm not teaching it today. I'm holding off on that. 7 go into it? I'll give you a hint. No. So none of the factors of 7 go into it. So that eliminates quite a few. 8's even. 9 is a multiple of 3. 10, we already said, is a multiple of 5. 11? Go into it? No. 13 almost does. It has a remainder of 1. Nope, we need whole numbers. 14's even. 15 is a multiple of 5. 16's even. 17 is prime, so we need to check that one. Does 17 go into 5, 4, 6, 1? Check it on your calculator. 17? Nah, it don't. Do we need to check 18? No, it's even. What about 19? We need to check 19? Yeah, it's prime. Check 19. Nope. We need to check 20? Need to check 21? How about 22? How about 23? Yeah, I gotta check 23. Check 23! No to 23. We need to check 24? Do we need to check 25? 26? 27? 28? 29. We need to check 29. Check 29. It's not 29. Don't need to check 30. Do we need to check 31? Oh, yeah. What is it?
We're
43 goes into it.
Yeah.
How many times?
127.
100. 100.
43 times 100 is 4,300, right? And then we've got 43 times 20 is 860.
Oh my god.
Peeling out. 43 times 7.
231.
Wait a minute.
It's not right.
No, it'll be 291. No.
Mm-mm. Can't be.
300.
Thank you. Got to be a 0 there. 301. That checks out. 43. So does 43 go into 16384?
Heck yeah.
It does? Yeah, I know. Does 43 go into 16384? Because if not, who cares?
No.
Are we doing another week of electricity?
This does not.
Not really. It doesn't. So 43, who cares?
Let's kill off 43.
Kill all 43.
I've lost your attention. All right, let's move on. 420. How about that?
It's like 4 minutes. So, Mr. Mac,
What?
is water wet?
Sometimes.
Elaborate.
What do you mean sometimes?
Water is not always wet.
Elaborate, Mr.
You ever
Mac.
met ice?
On your conjecture.
Have you ever met ice?
No,
Counterexample.
what's ice?
I win.
Vanilla ice?
Perhaps, or iced tea.
Ice, baby.
Here's what I'm gonna do. Take a piece of paper. Draw this. Go.
Go.
I'm gonna play a game.
We play games. You have cards.
No, I do.
We play blackjack. It'd be fun.
Yeah, but we're not here to have fun.
Hey, you can rest
Please. We have 2 parallel lines being cut by another line. What do we call that line? Transversal. Sounds like a wrestling move, but it ain't. I circled angle 1 and 5. Angle 1 and 5 are example of what kind of angles? Don't you remember the spooky movie? The spooky little video we watched?
The cat.
The CAP.
It's not cat.
CAP stands for corresponding angles postulate, which says if you have 2 corresponding angles, they are... I'm sorry, if you have 2 corresponding angles on 2 sets of parallel lines, then those corresponding angles will be congruent. Another way of saying that is, if a transversal cuts 2 parallel lines, the corresponding angles will be congruent. Key is parallel.
So we can figure out what if the
So 1 and 5 are example of corresponding angles, right? Corresponding meaning that they're in the same relative position. Maybe remember, not the same position, because that would be gross. If you're literally in the same position as someone else, we saw what happens when you drink that. What is it? Slam, like Kool-Aid Jammers. Yeah, it was like I don't remember, but it was great. 1 and 5 are corresponding, and they're on a parallel line, so that means we know 1 and 5 are congruent. Same thing with 2 and 6, 4 and 8, 3 and 7. Cool. There's some other sets of angles that we have not talked about yet. So we have some corresponding ones, right? We talked about that. So we have corresponding. I also want to draw your attention to this. If we have...
hold on, amigo.
I got it. If we have
Hold on, amigo.
2 lines being cut by a transversal, this automatically creates an inside-outside thing, right? So notice, this is the outside of the parallel lines. These 2 guys right here are sitting on the outside. Same thing down here. And then these guys are on the inside. We cool with that? We're going to call this external. Because they're on the outside. And then we're going to call this the internal, the inside. Anything inside is internal, anything outside is external. Go. So when I talk about these angles, I'm going to use these terms, internal and external. I'm also going to talk about things that are on the same side versus on opposite sides. And when I say opposite sides, what I'm going to use is the word is alternate. Okay? Or alternate. Alternate, it means to switch back and forth. So same side angles would be examples of like 1, 3, 5, and 7. They're on the same side of the transversal, you dig? Okay. Same thing with 2, 4, 6, and 8. They're same side angles because they're all on the same side. We have some angles that are same side internal. 4 and 6, right? They're internal and on the same side. We also have some same side external. An example of that might be 7 and 1. They're on the outside and the same side of the transversal. Small one stepping in?
Of course.
Okay. Alternate, like I said, alternating, would be an opposite side. So 3 and 6 are alternate interior angles because they are on alternate sides of the transversal and they are in the interior of the parallel lines. Okay? So, I'm going to draw your attention to alternate interior angles first, I think. So alternate interior angles. Examples of those would be 3 and 6, 4 and 5. 3 and 6 go together. 4 and 5 go together. Cool. Those are alternate interior angles. Opposite sides, alternate, right? Interior on the inside. We also have alternate exterior angles. Examples of those would be like 1 and 8, alternate sides of the transversal, external. 2 and 7, alternate sides of the transversal, external to the parallels. So we talked about alternate interior, alternate exterior. Let's talk about same side interior. Let's use light green. Same side interior angles. Somebody give me an example of same side interior angles. I haven't taught you them yet, but give me an example. Same side interior.
4 and 8.
4 and 8 are both on the same side of the transversal, but are both in the interior.
Ooh.
No! One's on the exterior. Same side interior angles. Somebody give me an example other than Danny. Yeah, go ahead. 4 and 6. Same side interior. There's only one example on this side. The other example would be 3 and 5.
I was thinking they had to be like equal.
Nope.
One is acute and one is obtuse.
So those go together. Those are same side interior.
Same side
Cool. We've also got same side exterior. Give me an example of same side exterior. Autumn. Same side exterior angles. Exterior means on the outside. So pick a number, 1 or 2. 1, okay, cool. So here's 1. That's same, we need same side exterior. So we already found an exterior angle. Autumn, which angle down here is exterior and the same side as number 1? 7. So those two are going to go together. I'll do a little symbol like this. Square and square. Whereas same side exterior on the other side would be 2 and 8. They go together, right? So we got alternate exterior, or interior, same side interior. We've got alternate exterior, same side exterior. I miswrote something. That should say exterior. Right? Same side exterior. Yeah. Nope, same side interior. I had it right before. So we have alternate interior, same side interior, alternate exterior, same side exterior. We also know about vertical angles. Remember those? Vertical angles? Right? Your words, not mine. It's two angles that scissor each other, right? We have the top portion and the bottom portion. They're always going to be equal. So check it out. 1 and 4 are examples of vertical angles by scissor theorem, right? Scissor means that we have two lines that are intersecting, any two lines that are intersecting. The top and bottom are always going to be the same angle. The left and right are always going to be the same angle. It's just a fact of life. If I change the angle of intersection, notice the top angles change too. Same thing with the sides. The sides are always the same. The top is always the same. That's vertical angles theorem. Scissor theorem, if you will. Your words, not mine. Vertical angles theorem. What do we know about angle 1 and angle 2? What are they? Zayden.
Linear pair.
Linear pair. Very good.
That means they are on the same line, which means
Two angles, same line. Yep. Which we can prove by linear pair theorem that they must be supplementary, right? So, let's take this big old list and let's talk about what we know. If these are parallel lines, okay? If that is true, then what do we know about these different types of angles? Well, corresponding angles are going to be what? Corresponding angles are always going to be what? Here's an example of corresponding, right? 1 and 5. Zayden. They're always going to be congruent because corresponding angles theorem, right? By theorem, I mean postulate, cap. Corresponding angles postulate says if transversals cutting two parallels, then the corresponding angles are going to be congruent. Cool. What about alternate interior angles? Well, we have a theorem called the alternate interior angles theorem. What are they going to be? We're going to prove that next time. Hang on to this diagram.
that's
See you tomorrow.
so no HW.
No HW today.